Example 7.4 or 8.4 for the given textbooks. For details, please see the description below. A piston cylinder device initially contains 3-pound mass of liquid water at 20 psi and 70 degrees Fahrenheit. The water is now heated at a constant pressure by addition of 3,450 BTU of heat. The goal of the problem is to determine the entropy change during this process. In order to solve this problem, we need to find the value of the entropy at both states of the process. In the first state, we have the pressure and the temperature. Therefore, we will be able to find the value of the entropy. However, for state 2, notice that the only quantity that is provided is going to be pressure. Therefore, we need a second quantity in order to find the value of the entropy at that state. What we're going to do is we're going to use a balance of energy in order to determine the second quantity that we will need. So we have the amount of energy going in, the amount of energy leaving is equal to the change of energy in the system. This is a closed system. The only quantity that we have going in is the amount of heat going in. There is no energy leaving, so this is equal to 0. And as I said, this is a closed system, so the change of energy that you have is going to be an internal energy. And this is a piston that is allowed to go up and down and is held at constant pressure. So we're going to have boundary work, which is simply P dV. And as we recall, this is equal to the change of enthalpy. So what we are going to find is that the amount of heat going in is basically going to be equal to mass and the change of specific enthalpy. So if we're able to find the value of enthalpy at the first state and using the value of heat, we could find that the enthalpy at the second state, and that would allow us to find the value of the entropy at the second state to be able to solve this problem. Now let's proceed to find the value for enthalpy and entropy for state 1. We go to table A for E in order to find the temperature of 70 Fahrenheit, and we have a saturated pressure of 0.36334 psi. Our working pressure is 20 psi, which is larger than the saturated pressure, indicated that the phase is a saturated liquid. Therefore, we will be evaluating at the values of the saturated liquid using the temperature table, such as this one. So we're going to go across and we're going to find that the value for the enthalpy is going to be 38.08 BTUs per pound mass. And we go across and we find that the value for the entropy is going to be 0.07459 BTUs pounds mass Franklins. Now that we have the initial value of the enthalpy, we could find what is the final value using this equation. So we simply solve for H2. So the heat going in divided by the mass plus the initial enthalpy will be equal to H2. The initial heat is 3450 BTUs. The initial mass is 3 pounds plus the initial enthalpy is 38.08 BTUs per pound mass. And if we add this to term, we find that the final enthalpy is equal to 1188.1 BTU per pound mass. Now for state 2, we have the value of the pressure as well as the enthalpy, so we could go to the table to determine what phase do we have. So we go to the table, and for a pressure of 20 psia, and we go and evaluate the values of enthalpy, and we have that the value for enthalpy that we currently have is 1188.1, which is larger than the value of the saturated vapor value for enthalpy. This indicates that for this state, water is a superheated vapor. Now we go to table A6E for superheated vapor, and we go to 20 psia for pressure, and the value that we're looking for is for enthalpy, and is 1188.1, and is between 11 81.9 and 12.01, which correspond temperature between 280 and 320. So we're going to do interpolation between these two values in order to determine the value of entropy at this particular state. These are the values that were obtained from table A6E. With these values, we are going to interpolate, and we find that the value of temperature 2, which is between 280 and 320, it's calculated to be 292.85 degrees Fahrenheit. And if we do the same interpolation process, we find that the entropy at that final state is equal to 1.7761 BTUs pound mass Rankine. Now that we have the final value of the entropy, we could find what is the total change of entropy during this process. That is simply going to be the mass and the difference between the specific entropies that we calculated. So we have that the mass for this process is 3 pound mass. The final entropy is 1.7761. The initial one is 0.07459. Both of them have BTUs, pound mass Rankine, pound mass and pound mass cancel out. And we find that this value is equal to 5.105 BTUs per Rankine. This is the TS diagram for this problem. Notice that we start as a compressed liquid at state 1, and then we end up as a superheated vapor. The lines drawn from point 1 to point 2 are done at constant pressure.